Okay, now we're going to look at AP topic 9.8. We're staying in polar form, but now what we want to do is we want to find the area of a region bounded by a polar equation, so a single polar curve, and bounded by two different angles on that polar curve. So just real quick example, suppose we have a polar curve that does something like this, and we want to find the area of the region from 0, when theta is 0, to pi halves. And so, essentially you're integrating, which is finding an infinite number of slices from 0 to pi halves and finding the lengths of all those and to find the area. And then be like a sort of like a pi r squared. So reading on before we do an actual example, you might also be asked to find parts of polar equations that you might know, like a single petal of a rose curve, or they might say the outer ring of a limacon, or one curve of a lemniscate. And anytime it asks you to find something like that, you will need to figure out the bounds. So you'll need to figure out the lower bound and the upper bound, the thetas, the alpha and beta in this example. And those will either be given to you in the graph, or you're going to have to find those bounds with your graphing calculator and figure out where those parts start and stop. Now, one more other thing that is just slightly unfortunate, because in all of AP Calculus, A, B, and BC, you've not really had to use these, but this is one time when we might have to use these two particular half-angle identities. And I'm actually going to show you an example that uses a half-angle identity in it. Okay, so here we go. Let's do an example. And so I'm going to get rid of all that. And here's what we want to do. We want to find the area of this lemniscate. Let's see, let's do r equals 1 plus 2 cosine of theta. And we want to find the area from theta equals 0 to theta equals pi halves. All right, here's a picture of, actually here's a picture of this lemniscate without stopping at pi halves. And then if we're going to stop at pi halves, we only want that area. So going back to the pole, back to the center, the origin, we're going to find all of the shaded area that goes from the origin out to that curve. Okay, so here we go. The formula is 1/2 of the integral from the lower bound to the upper bound of the function squared. And then you're going to take the derivative of it. So let's set this up. Okay, here we go. My area is going to be 1/2 the integral from 0 to pi halves. And that's going to be of our function 1 plus 2 cosine of theta, all squared, d theta. Okay, so let's clean this inside up by multiplying through 1 plus 2 cosine of theta by itself. So if we're going to square it, we'll get 1 times 1 is 1. 2 cosine of theta times 1 plus another 2 cosine of theta times 1 is 4 cosine of theta. And then 2 cosine of theta times itself is 4 cosine squared of theta. All of that gets a d theta. And I want to split these integrals up into separate integrals. So 0 to pi halves of 1 d theta plus 1/2 of 0 to pi halves of 4 cosine theta plus 1/2 of 0 to pi halves of 4 cosine squared theta d theta. Of course, it's 1/2 times all three of these terms as separate integrals. You could bring the 1/2 out to the very, very front and multiply everything to it. Just be careful that you don't forget to do that if that's what you do. Okay, so starting out here at the beginning, integrate the number 1. We're going to get turn it into a theta, and we're going to evaluate that from 0 to pi halves. That'll be pretty easy. Integrate the number 4. Well, we can, we have 4 cosine of theta. We can bring that 4 out front to the 1/2 and make that a 2. So this is going to be plus 2. The integral of cosine is sine theta, the antiderivative of cosine is sine. And, oops, no d theta. That's going to go from 0 to pi halves, so 2 sine theta from 0 to pi halves. Now, this is where we're going to have some fun here. The integral of cosine squared. Okay, so we do have a half angle identity here on the top left of your screen. That cosine squared theta is equal to 1 plus cosine of 2 theta. That's a terrible looking thing. I'm such a sloppy writer. 2 theta over 2. All right, so we're just going to kind of work on this integral for a while, kind of over here. So that'd be 1/2 0 to pi halves of 4. Let's just bring that 4 out to the front like we did on the other one. So 4 times 1/2 is 2. So then we have 1 plus cosine of 2 theta over 2 d theta. We can actually divide that 2 out to the front as well, so that makes all that much, much nicer. So we just have the integral from 0 to pi halves of 1 plus cosine of 2 theta d theta. All right, so we can integrate that pretty easily. We could separate it out, and so you get the integral of the antiderivative of 1 there in terms of theta becomes theta, evaluated from 0 to pi halves. And then the integral of cosine 2 theta, well, it's going to become sine 2 theta. Then you have a little bit of u substitution in there, so sine 2 theta divided by 2 is what that would become. So that if you're taking the derivative of sine 2 theta, that 2 coming out cancels out the 2 on the bottom. So putting it back over into our problem, we should have plus theta evaluated from 0 to pi halves plus sine of 2 theta over 2 evaluated from 0 to pi halves. All right, so now we're ready to go to town here on this work. Let's switch colors here. We'll go with an orange. All right, so this is 1/2 of pi over 2 minus 1/2 of 0. The 0 doesn't matter. Plus 2. Well, let's see. Sine of pi over 2 is 1. Minus 2 times sine of 0 is 0. It doesn't matter. Plus pi over 2. And minus 0 doesn't matter. Plus sine of 2 times pi halves is sine of pi, which all comes back to 0. So that becomes 0. Then you subtract out the 0. It doesn't matter. All right, so what do we have? We have pi fourths plus 2 plus pi halves. Get a common denominator, and we can call that 2 plus 3 pi fourths. And that is the evaluation. That is the area of that polar curve from 0 to pi halves. And it's kind of a mess. And you really hope that this is a calculator problem so that you don't have to do that all by hand. And if it is a calculator problem, then you can put all that in and let the calculator do that hard integration. You don't have to know the half angle identity over there on the right side of the screen that we worked out in black. But if it's doing it by hand, then you memorize those two. You need to know those two half angle identities. All right, so back to our curve here. If we shaded that area in from the pole out to that curve from 0 to pi halves, our answer rounds to about 4.356, and that's how many units we would have shaded in there, and that looks accurate to me. All right, so there you go. That is AP topic 9.8. Good luck.